Something strange. A red button is flashing. Is that normal? How about this? Good. All right. What is this? When relations have some interesting properties, it's worth noticing, and that gives us a little flexibility with those relations. So what is it? We say that relation R is reflexive if for every x from A we have xRx. One. So if every member is related to itself, then relation is reflexive. And immediately it's a good idea to have a line of example. If you look at the lines, line A parallel to line B, do you think that relation is reflexive? Is line parallel to itself, yes or no? For every line, that's true, so that's a reflexive relation. Being equal is also reflexive. What about A less than? How about being perpendicular between the lines? Is that a reflexive relation? Is every line perpendicular to itself? No, so that's not reflexive. So some relations are reflexive, some of them are not. R is symmetric if we have the following, if for every x and y from A, if they are related in one order, then they are related in the other order as well. So what is this telling you? They are either not related at all, or they are related both ways. What else? R is anti-symmetric if completely the opposite thing happens. Although you might be surprised with the way how we'll say it if the following, if for every x and y from A, you don't want them to be both. It rarely is both. The only way you have it both ways is when you are related to itself. So if x is related to y and y is related to x, that's only allowed if what? X equals y. This is just to allow reflexivity for those. Basically, you are saying if you are two different... Oh, by the way, we are skillful enough to say this also differently. Can we do contraposition of this? Yes. So what? If x is not equal to y and x is related to y, then what? Since you cannot have both. Y is not related to x. Exactly. Not true that y is related to x. So for two different objects, if one way they are related, they cannot be reversed. In the way irreversible, except with itself. Very important one is when R is transitive. What is that? It's for three objects. For every x, y, z from A, x r y and y r z implies x r z. So this just fixes vocabulary. Maybe the easiest way is to see this on a diagram. So on a diagram, when relation is reflexive, let me draw a few pictures. Is this relation reflexive, yes or no? Just pay attention if every element has that little loop around itself. Does A has a loop? B? C? You don't care about anything else. So if there are some connections or not, doesn't matter. What about symmetric? Symmetric is also easy to check. If I have A, B, C, and then if I have an arrow from A to C, I must have also what? C to A. Then if I have A to B, I have to have it from what? B to A. Let's say something like this. If it's missing both ways. And let's say, what if B is reflexive as well? Doesn't hurt. So that symmetry is automatic. So here is something that's symmetric, it's not reflexive. What about anti-symmetric? Generally, it says the following: if you have A, B, C, if you have it from A to C, you can have it from C to B. The only one that's not allowed is which one? A reversal. You cannot have C to A, you cannot have B to C. Transitive is probably the most interesting one. Generally, it works the following way. By the way, I'll talk about examples later. So if I have A, B, C, then if I have arrow from A to C, and then if I also have arrow from C to B, so if there is continuation, it must be continuation, then there is a shortcut between what? A and B. So generally, you always close the triangle whenever, like when you add up the vectors. You remember how you add up the vectors in Calc 3? One vector, then the other one, then you just close the connection A plus B. So whenever there is connection from A to, so generally you can say the following: whenever there's a path from A to B via another point, there is a direct connection. You are closing the triangles. Yes?
In the number 3 picture, could there be an arrow that goes from B to A and it still would be anti-symmetric?
Yes.
It wouldn't count then?
No. Only direct connections count. Don't do multiple paths. So just direct connection is the only thing that's related, not via something. Yes.
We're saying if A goes to C and C goes to B, and there's a line, then it's transitive. Not necessarily if it goes, then it's transitive.
No. To be transitive, you need to satisfy the following property. Whenever you have A to C and C to B, you must have A to B. If you lack this, you fail transitivity. That's what it is. So that's what it says. If you have those two connections from X to Y and from Y to Z, then it's X to Z. Let me ask you the following to make it sure that we understand this drawing. What about this? Is this relation transitive? It is. Why? Not every triangle has to be closed. It must be closed triangle of continuation. Look at this triangle. A goes to C, and then what? Continues from C now. And this is not that. So do we have any continuation here? No, you don't. So there's no, it's not necessary to have closure, so this is transitive. Because if you disagree with me, give me counterexample. Give me a value for X and value for Y and Z, so that these two are true and this one's false. How much is your X in your counterexample?
Is there an A to B in there?
What's A?
Is there an A to B in there?
No, here it is.
We're just talking about A to C and B to C.
Yes, so here is complete relation. A is related to C, B is related to C, and nothing else. So is this transitive? The answer is yes. Why? Because you cannot find me counterexample, because to make counterexample, you can start with A and take ARC, but now you would need C to something, do you agree? But C doesn't go to anything, so you cannot make me counterexample on the left side, and that's it. So be careful. It's not about closing any triangle, but closing triangle in continuation. If it was like this, then what? Would this be transitive? No, unless you close it at A to B. Is that clear? Yes.
So, wait, the transitive statement is true, but the integral is not necessarily true.
What do you say? What do you say?
Because the left side of the arrow is false, then the whole statement is true, right?
Exactly. Yes. So my relation is transitive. Yeah.
But even though the whole statement is true, the end statement isn't necessarily true?
No, it is. So whatever you X, Y, Z you choose, generally your left side will fail because you cannot make continuation. So it's what we said vacuously true universal statement. You remember those? If you cannot, because the only way you can find me challenge, if you can find X, Y, and Z is to make this true and this false, do you agree? But you can never make this true because that's how it's designed. So this is always false and this is always true, and I'm okay, relation is transitive. So this statement is always true no matter what values for x, y, z you make. If you want, I'll write them all options. X is this, y is this, z is this, and then whenever you do the calculation, true, always. That's fine. That's fine. Think about it. It'll settle down. All right. So let's play, and that's it. The whole section is about playing with these guys when a relation is given different ways, either as a list, either as a table, either as a diagram, to see how they look, if we can recognize and everything. Yes?
What is the one that you drew next to transitive? Is that antisymmetric or what is?
Which this one?
Yeah, right there.
This one?
That's not transitive, right?
It's not, because if you want it to be transitive, you must close this. So that's why I made it dotted. So to say those were there, this one needs to match up, yes.
That arrow could go either way, right?
No, it has to go from the beginning of the first one to the end of the second. Like for vectors, the same thing. When you add up two vectors, you add like this. One goes like this, second one is this, and then you make a shortcut from the first to the second. Beginning of the first to exactly the same way. All right, let's see a couple of examples. Here's a relation. Do you think it's reflexive, symmetric, transitive? If we have a list, what do we need to do? Reflexive is easy to see, don't you agree? What? You are looking if all the diagonal, those are called elements on the diagonal on the table. So 1, 1 is there, 2, 2 is there, 3, 3 is there. 4, 4 is not, so it's not reflexive. Is it symmetric? You look someone outside of diagonal, like a 1, 2, but if 1, 2 is there, but who's missing then? 2, 1, so it's not there, so it's symmetric. So we keep finding counterexamples. Is it transitive? So is it transitive? I don't know. Transitivity is the hardest one to see. So the only way to see it, from the table you cannot see it. From the list you cannot see it. The only way you can see it when you make a diagram. So for this one, to see if it's transitive, let's do the diagram. So what is it? There are 1, 2, 3, 4. One sense, okay, these three have these little loops. 1 goes to 2, 2 has a loop, 2 goes to 3, 3 goes to 2, so there is that little symmetry there. 3 stays, 3 to 4, 4 to 3, 3 to 4, 4 to 3. Is it transitive? No, what's missing? Tons of things are missing. What's your counterexample? 4 to 1? I don't see 1 and 4 involved anyhow. Is there 1 and 4? No. No. So, but this is missing. 2 ascends to 3. 3 continues to 4, but 4, 2 is missing. Do you agree? So 2 are 3, and 3 are 4. Should implies 2 are 4, so this is true, this is false, so the whole thing fails. Oh, here is one tricky example. This is not so easy to see. Is this relation transitive?
It's 1, 1, 1, 2, and 2, 2. But
So is it transitive or is it not?
Do you need 3 elements for it to be transitive?
Yes, no, to challenge it. So generally, the question is, so if I don't have 3, whatever you have, so nobody says here that x, y, and z must be different, don't you agree? So some of them might be the same. So generally, what? Probably with only 2 elements, I have less chances to make a counterexample, do you agree? But still I might, because here it is. Sometimes people see, I don't see a triangle, nothing can go wrong. That triangle could be a tiny triangle where 2 of them are the same. Lee, do you have a question, a comment, a suggestion?
I just thought that for 2 elements, proving if something is transitive would be essentially the same as proving that it's reflexive. Because to me, the only way you can go is
Not really.
back and forth between 1 and 2.
Let me see. So, so what? So obviously, I cannot choose all 3 of them to be different. Do you agree?
Right. But if you
So 2 of them are the same. So here it is. So what? But generally, what if I have what? 1R1. And then what? If I want continuation, I need to do 1R2. But generally, if those are the same, then the only thing I need is the third one. Do you agree? So generally, if I write all the possible cases, it looks like it's going to be transitive. But it's always a little risky. If probably you should just do all the options for x, y, and z. This one has 2 options. This one has 2 options. This one has 2 options. So there are how many options? 8. Write them all. 1, 1, 1, 1, 1, 2, 1, 2, 1, and then, some bulky analysis. So everything should be okay. But let me see the following. Suppose I have a relation like this. Suppose I have a relation like this. And suppose I have something like this. Here is 1, here is 2. Is this transitive?
I would say
Again,
2, 1, 1, 2, not 2.
here it is. Very good. Look at this triangle. Does 2 go to 1, yes or no? 2R1. And what? 1R2 should imply what?
2R2.
What's happening? 2R2 is missing, so is this transitive or not? Not transitive. So this is just a little warning for degenerative cases where even you cannot see the triangle, transitivity might fail. And someone, actually Lee, I think, mentioned it that way. If you have a transitive relation, and if from every node to every node there is one connection, it has to be reflexive as well, exactly because of this written here. All right. So these were little details about transitivity. Let's see. Oh yes, this is the graph of this one, and then even without graph we're able to answer the question. What about this one? 622. Any comments on this one? What is this, by the way? The only related things here are just these little loops. Do you agree? What is this? What kind of relation is this?
Reflexive. Because it's transitive.
What's it?
It's reflexive because they're all to themselves.
Actually, this is the most famous relation of all. What is it? One is related to what? To itself. What about 2?
Just only related to itself.
So what kind of, how do we call that relation? Or equal sign. So generally R
Oh.
is actually equality. Equality is the most famous relation. That's what? Is it reflexive? Every number is equal to itself. Is it symmetric? If number A is equal to number B, B is equal to A, and if A is equal to B and B to C, A is equal to C. Those are very important properties of equality that we take for granted in calculus and we use all the time, but generally those are properties. But here is the big thing. That equality actually served very much as motivation for everything that was done about relations, particularly for relations of equivalence that we'll discuss immediately after the break. So equality is a very special relation that has what? Just reflexivity and nothing besides that. So object is only equal to itself. What say?
Isn't it also symmetric?
Of course, it is symmetric, it's transitive, everything it is. So that's the famous one, the first one that was analyzed with all these three properties. So equality is both reflexive, symmetric, and what? Transitive. What else? What about the relation of being parallel? Is it reflexive?
Yes.
Is it symmetric? If A is parallel to B, is B parallel to A?
Yes.
And then is it transitive? If lines A and B are parallel and B and C are parallel, like A and C are they also parallel? Yes, why? Because parallelicity is like equality of direction, because you are parallel if you have the same direction, do you agree? And equality has all three properties, so that's what it is. What's he? All right, so, and here is one of our main players. So this is the one that we'll actually particularly define after the break, but it's a good idea to connect it at this point. What is it? Congruent certain modulo. So example 624. This is a big example, and that's the one that will be crucial for Monday. So here it is. So first, what is domain? Z. So in all integers are here. And we say the following. M is congruent with N modulo 6 or any other modulo. So I just chose 6 as an example. And here is the definition. If 6 divides N minus M. If 6 divides into N minus M. You subtract two numbers, divide by 6, and if it divides completely, then you say they are related. First, is this a well-defined relation? Can you always give me the answer yes or no? Why? Because you take the difference. Every number has a remainder. So generally, if that remainder is 0, then you say yes. If it's something else, you say no. Agree? So my question is this relation reflexive, symmetric, and transitive? Is it reflexive? Question 1. Is it reflexive? And how do you check those abstract definitions? Don't try, to check how you feel about it. Just apply the definition, and definition will tell you. So what am I asking you? I'm asking you, is M congruent? We say congruent modulo 6. Is every number congruent with itself? Yes.
Yeah, because when anything divides 0.
Exactly. So I'll translate the question. If 6 divides into M minus M, which is if 6 divides into 0, and 6 does divide into 0 because 0 equals 6 times 0. I'm not saying that I'm trying to divide 6 by 0. I'm dividing 0 by 6. So since this is true, this is also true. Question 2. Is it symmetric? And that means if M is congruent with N modulo 6, is it the other way also true? Let's see. Give me some example. Are 3 and 9 related modulo 6? Yes or no? Are they related? How much is their difference? Is that divisible by 6? Yes, it is. So they are related. And then I'm asking you, is then 3 also related to 9? How is that different? When I subtract them and I'm not going to get 6, what will I get? Is it also divisible? Yeah, so answer is it is symmetric. Here's the proof. Assume m congruent with n. Then it means 6 divides into n minus m. Because that's what definition says. Which is equivalent with 6 divides minus of n minus m. Because we know if number is divisible, the opposite number is also divisible. Which is equivalent that 6 divides m minus n, which by definition means that what? When I subtract them, it says second related to first. So it's n congruent with m modulo 6. Why is this important? Because it actually shows us that this important relation that we'll use very often behaves like equal sign. So just it's symmetric. Is it transitive? Let's see. Question 3. Is it transitive? Again, what do I need to prove? Look at this statement. Assume that these two are true. Show that the third one is true. I'll just erase here so that we have a little more space. So here it is. I will assume that m is congruent with n modulo 6 and that n is congruent with some k modulo 6. What's my goal? To show that what? So how do I do that? I'll translate into divisibility and then try to connect. This by definition means that 6 divides what? N minus m. And also, 6 divides into k minus n. By definition, I'm just applying it. And here comes the only creative part here. How can I get something for k and m and get rid of n in a very easy way? What should I do with these two to get rid of n? How can I get rid of n from these two numbers? No, can I add these two numbers? Because if 6 divides this number and 6 divides this number, then 6 divides their sum. But what happens in their sum? N and n cancel. So I got 6 divides k minus m. By definition, that means what? That m is congruent with k modulo 6. So this relation is transitive. This is a very important relation. So we have a definition, and then by definition, we were able to show that it's reflexive, symmetric, and transitive. You will see very often in homework, for some abstractly defined relations, I ask you this question, and basically this is the technology. And also on the exam, that question appears very often. So it's important to have that little, and there wasn't really nothing, there wasn't anything special here. Just make the assumption, translate according to definition, and then do a little calculation at the end. And just one more thing, and I think, so these are all kinds of examples. We don't have to rush with this. This is a little too much. What about less than or equal? What are the properties of that operation? We're not going to write it on the board. Just tell me, what do you think about that one? Is it reflexive?
Yes.
Is every number less than or equal itself?
Yes.
Is 7 less than or equal 7? Yes. If it's strictly less, it would be no, but for less than or equal. Is it symmetric?
No.
It's actually what?
It's
Because if A is less than or equal B and B is less than or equal A, they must be equal. So it's anti-symmetric. Is it transitive? If A is less than or equal B and B less than or equal C, then A is less than or equal C. So less than or equal doesn't have, so usually we talk to 1, 2, 4. But less than or equal has property not 1, 2, 4, but 1 what? 3, 4. So there are two big alternatives, and you will see the rest of the chapter. Those are two directions that we'll analyze in this. And one more thing, just a little detail, sorry. Oh yeah, there's more than I thought. the question is, suppose we have a relation that's not transitive. Can you add connections to make it transitive? So how would you do that? So here's a relation on the example. So here it is 627. A relation R is 0, 1, 1, 0, 2, 3, and 3, 4. And it says here, find RT. RT is called transitive closure. So what is that? Minimal, of course, if you connect everybody, then it will be transitive. Do the minimal addition of connections so that it becomes transitive. So what would that be? So here is 0, here is 1, here is 2, here is 3, here is 4. Do I have connection between 0 and 1? Yes or no? And I also have what? 1 to 0. All right. And I also have 2 to 3. And I have 3 to 4. Is this transitive? No, it's not. So how can I enrich this relation? That means adding connections so that it becomes transitive. So I need something that's transitive, so everything has all the versions of traveling. So what should I do to make it transitive, but adding only what's minimal? How would I have to add? What would that be? 2, 4, you mean?
4, yeah.
Yes, so RT is R. R transitive is R union. Then what? 2, 4. I added 2, 4, but now here's the problem. When you add the new connections, you might open a new crisis. Do you understand that? So don't think that once you add whatever's missing, because now you have more candidates for triangles, by building new, you might open new crises, but that didn't happen here. So here, by adding 2, 4, nothing open, so here everything is closed, so everything is okay. What about here? 0 to 1, 1 to 0. What? Do I have continuation here? Yes or no? What do I need to add as well? 0, 0, as we mentioned. So I need 0, 0, and I need what? 1, 1. Is this now transitive? Yes. Now it is transitive because from this block, of course, there's no connection between these two blocks. So if both blocks are transitive, everything is transitive. 2 to 3, 3 to 4, 2, 4 closes. There's nothing else here. I showed you this trick. When you have symmetric, actually transitivity also makes reflexivity, and that will be transitive closure. So every relation has a transitive closure. It's intersection of all transitive bigger relations, but this is the way to do it internally. All right, so that was the story about these properties. As I said, probably the most interesting and the least trivial is transitivity. The others are fairly simple. All right, let's take a break. We continue at 47.